So because I forgot to start the recording at the beginning of class, I'm going back and talking about it now on what exactly is going on here. Today's lesson is on double integrals in polar coordinates. Now, we've been talking about integrals as far as the base being a rectangle, which we called R. We talked about where the base is some unusual shape, which we called D. This one is talking about when the base is circle or something that can be described well in polar coordinates. So the base is in polar coordinates.
Good afternoon. It is now 2:30, and if you are not with a teacher, coach, or sponsor, please exit the building at this time. It is now 2:30, and if you are not with a teacher, coach, or sponsor, please exit the building at this time. Have a great afternoon and weekend.
Or in a circular shape. That's the best way to describe it. So the bases in polar coordinates are in a circular shape. So the setup of this is a little bit complicated, so I'm just going to kind of give the basics, and then I'm going to pause it and then catch up with where the recording from class was. So what's happening here is we're first of all remember that polar coordinates are in terms of r and theta, and r is how many radiuses you go out. So it could be 1, 2, 3, 4, 5, 6, 7. And then theta is how big of an angle you sweep around when you graph. Okay? So the region that we're dealing with is measured in terms of r's and thetas. And we call this thing a polar rectangle. Now, it's not really a rectangle. I'm talking about this thing right here. It's not a true rectangle, but they call it a rectangle because two of the sides are straight. And two of the sides aren't straight, but they're defined in terms of constant values. This is when a radius is, say, 1, and this is when a radius is, say, 3. So they're constants, and that's why they call it a polar rectangle. For definition of the equation, however, it is looked at more like a trapezoid than it is a rectangle. So we'll talk a little bit more about that in a minute. So basically what happens is this over here that I'm coloring in right now, this is the base over which our upper curve is hanging. And it looks like a piece of a washer. That's a good way to describe it. It's a piece of a washer. So what we're doing is we're taking that region there and we are dividing it into smaller pieces. Okay, just like we did the rectangle. We divided the rectangle into smaller pieces. And what the middle one shows the left one divided into smaller pieces. The right one shows a blown up version of the left one. Now, the way they define this is with this formula down here. We have, they want you to remember that in a circle of radius r, the length of an arc subtended by a central angle of theta is s equals r theta. That is a formula that you learned in either geometry or pre-cal. So in terms of this right here, S is this length of this arc right here. And it's defined by how wide of an angle we have and how far out from the origin that we are. So S is the arc length, and r and theta, r being the radius out from the origin, theta is how far of an angle that we go. So this is an S value here, and this is an S value here. Okay, but we're going to talk about it in terms of r and theta. So the distance between the smaller one, I'm going to try to use two different colors here, and the bigger one up here, that is delta r. It's the change in the radius, because the radius is defined from here outwards. So the change in radius from this point here to this point here is delta r. The change in angle across the radius is delta theta. So what we do is we take a look at this as a trapezoid with parallel sides. The first side is this, and the second side is this. These are ways of writing S. Now, what is the I minus 1 and the I? The I is how many radiuses I went out. Let's say that this one over here is 1, 2, 3, 4, 5, 6, 7, 8, 9 radiuses out to the outer edge. So this is like R9 with an angle of d theta. And this one would be R8. The inner one, this is R9, this is R8. So that's R8 d theta. Now the delta theta, the angle for both of these S's are the same. That's why this d theta is the same for both of these regions right here. Okay? Now, all this is doing is setting up the formula that we're going to use later. So if you don't completely comprehend this, that's okay. But what you do need to know is that we're going to go off the formula of a trapezoid, and the trapezoid is 1/2 the height times the sum of the bases. Now the height is the height between here, notice where I'm coloring on the big one, to here, and that happens to be delta r. So we're going to change this to be 1/2 delta r, and B1 is the first S, and B2 is the second S. So it's R I minus 1 delta theta plus R I delta theta. And that formula is this formula right there. That's the exact same formula. So that's how they went from the trapezoid geometry formula to the one in terms of this picture that we're dealing with up here. All right, now the next step is to look at this thing right here. Okay, or even let's actually go back to the one that I wrote down. That's a better picture, so I'm going to erase that line I just drew. Looking at the one I just wrote down, what can you factor out of the parentheses that they have in common? Well, they both happen to have a delta theta, so I'm going to pull that out. 1/2 delta r delta theta, r I minus 1 plus ri. Okay, and then, just like mathematicians do, they take what they want out of that formula and they call it something else. They called it r star, this r star thing. And it's got r star with an ij. I like to just call it r star, and I talk about it on the next screen in terms of r star. It's the 1/2 and the parentheses. So I'm going to come over here and highlight that. 1/2 and the parentheses is r star. So what have I not highlighted? I have not highlighted the delta r and the delta theta. Well, I don't like that with a highlight. Let's do this. I have not highlighted the delta r and the delta theta. So now take that and come to here. Do you see how this thing, the highlighted stuff, turns into the r star, and the delta r and delta theta come afterwards? Now, this r star, if you go to the next page, is right here. R star, delta r, delta theta, and delta a right here. And from this point, you're going to pick up the class video to watch the rest of this. Here we go. So the previous page, we found out that this thing right here, now remember, I can hear background conversation. Found out from the previous page that this thing right here is the same thing as the area of the base. Rij, delta r, delta theta. Then they come down here, they put it in a Riemann sum, right here, and then they take the limit. Okay, so let's talk about this. We don't care as much about the Riemann sums. What we care about now is the integrals, okay? Notice how this integral looks. The double integral, let me change colors here. The double integral over a polar region can be expressed as an iterated integral in polar coordinates. So in other words, if the function, notice that that says f of r comma theta. That means the function is already polar. And it's over a region R. We call it an R. We talked about this last class. If it's a little d at the bottom, it means it's a non-rectangular region. These are being called rectangular regions. So they're back to R's. Okay? So it's going to be dr d theta all the time, folks. Remember in the past we could go dx dy or dy dx, it didn't matter. These are always dr d theta. Okay? So I'm going to write that down.
It is always in this order, dr d theta.
Not changeable at all.
Not changeable at all, because you never, when you have an equation in terms of x and y, it's very easy to, if it's already in terms of y, to solve it for in terms of x. But it's very difficult to do that in polar. Almost 99% of all polar equations are r equals something. And it's really hard to switch it around and make it theta equals something. It's just too much pain to do it. But what I want you to see is the fact that this has an r right there. An extra r jumps into your integral every time. That is so, so, so important. And that extra r is this r up here. The r star is what your extra r is. Okay? So when you do these, you don't have to think, should I put x's first or should I put y's first? Remember that when you do double integrals, the constants go in the first integral and the equations go in the second integral. Same thing is true here. The constants will always be your thetas. Your angles never change. These are your constants, and these are your equations. And once we do one, it'll make a lot more sense. Okay, so today in this homework, you're going to see two types of problems. You're going to see problems that are already in polar, and you're going to see other problems that are in rectangular that you're going to have to change to polar, using those rules that you learned way back in pre-cal. Okay, when we get there, we'll put those rules back on the paper so that you remember what they are. So, down in the next section, it gives you what to do is to change it into from rectangular coordinates. I don't like the way they said this. So if it's already in x's and y's, you may find it easier to change it to r cosine thetas and r cosine thetas. And this is kind of a synopsis of what's coming up. We're going to start with all polar, and then we're going to go switch to rectangular equations. Now usually you're not changing, well, yeah, you are sometimes changing the base, but usually it's the upper equation you're changing. So pretty much, once we get it all set up, we do it exactly like we did the other problems. We do the first integral by hand, and then the second integral, once we get it down to one variable, we throw it in the calculator and use the calculator to do the rest. All right, next page. Here's where the rubber meets the road. Okay. Sketch the polar region. They already give you a picture. This one's already done for you. They tell you what r is. R is from 1 to 3, and theta is from 0 to pi. R is from 1 to 3, theta is from 0 to pi. So, what region is that really talking about? As you can see from this figure down here, r equals 1 and r equals 3 are circles with a radius of 1 and a radius of 3. Does that make sense?
Yeah.
Okay. 0 to pi is angles that go from here over to there. So that's why we color in that half of a donut, and that's the region that we're talking about. That's the polar region. So if I went ahead and gave you an equation to go above it, you could integrate it with that. And that's what we're going to do in the next problem. Come on. Scroll, scroll, scroll. All right. Now, go to the bottom of the page. Now let's actually do the math. This is slightly different. They tell us we're going to use the problem region R 3x dA over the region 1 to 2 for R, 0 to pi for theta. All right. So here's how this goes. You're going to do a double integral. Theta always comes first. So we say theta equals 0, theta equals pi, and then the R one. R equals 1, R equals 2. Now, I know they're both constants, but we're going to go ahead and be consistent. We always put theta first and R second, because later on, R is going to be an equation like 2 cosine theta, or 3 sine theta, or something like that. Now, when we put this in, we don't want to put 3x because there's no x's on our integrals. How can we change x into r's and thetas? X equals r cosine theta. So, good. X equals r cosine theta. So 3r cosine theta And remember that dA includes an extra r. It's RD theta. You got to put all of that. Otherwise, you're going to get the wrong answer. dA in this case is RD theta. I just feel like I'm laughing. RD. R. Okay? Yes, laugh at Miss Bell. It's time to do that. Okay, now, so now we're going to cordon off the dr stuff. Okay? I'm going to rewrite this problem. Theta equals 0, theta equals pi. R equals 1, R equals 2. 3r squared cosine theta dr d theta. Okay. Now remember, the first integral, r is the variable, theta is the constant. So what is that antiderivative going to be?
What is the R?
R is the variable,
Oh,
theta is the
sorry.
constant.
Right. So that be R, the R cubed.
R cubed cosine theta. Cosine theta just sits there. So we write theta equals 0. I didn't mean to change colors. Let's go back. There we go. So theta equals 0. Theta equals pi. This will now be r cubed cosine theta from r equals 1 to r equals 2 d theta.
What?
Cosine theta is a constant.
You took the anti. I thought you were
Took the
plugging it.
antiderivative. Yes, I did. Okay. Can you plug those in your head?
Yeah.
2 would be, if I plug in a 2, I'm going to get what?
80.
8 cosine theta. If I plug in a 1, I'm going to get 1 cosine theta. So when you subtract those 2, you're going to get 7 cosine theta. So to save myself some writing, theta equals 0, theta equals pi, 7 cosine theta d theta. Okay. This one, theoretically, you could go straight to the calculator. However, this is a very easy problem. In the time that it takes you to go search for your calculator, I can have this one done. Okay? What's the antiderivative of 7 cosine theta?
Negative 7 sine theta.
Almost.
Positive 7 sine theta.
Positive 7 sine theta
Oh,
from 0 to pi. Now I'm taking off the theta equals now because I'm down to one letter. So I get 7 sine pi minus 7 sine 0. So what's the sign of pi? No, it's 0. What's the sign of 0? Oops, I wrote theta instead of 0. That's a 0. Oops, here we go. Sign of 0 is 0, so the answer is big fat goose egg, 0. Okay, that's very weird, but it's right. Questions?
Nope.
Okay. So I want you to just set up 517. Set it up.
Say less.
Don't worry about working it, just set it up.
Say less.
This is to make sure I get through the notes. Look at the screen when you're done, see if you got what I got.
R squared.
what?
Why'd you? Oh, no. Dang it, I forgot the.
Oh, I just didn't write that. Yeah.
Rip.
If you wrote r cosine theta, RD theta, that's fine.
Yeah.
I didn't.
but it is r squared cosine theta d r d theta. Just always remember you raise your r's one guy, one power. It's got to be r d r d theta. Okay? How are we doing? Good on setting it up. Theta's first, r's second. Changing x to r cosine theta. Remembering r d r d theta. Turn the page. Next. Okay. This one, because I moved it, kind of got messed up. This parentheses that's between the 1 and the minus is supposed to be in front of the 1.
Wait, what?
This-
1 minus x squared.
Yeah, it's supposed to just be 1 minus x squared minus y squared. I apologize. I didn't catch that till after I ran them off. PDFs are so hard to edit. They are a pain in the backside.
Oh, wait, I don't have.
Okay, now notice here, it says R is the unit circle. It doesn't give me intervals for R and theta. I have to come up with them.
R is 0 to 1.
Yes?
Then theta is 0 to 2 pi.
Oh, wow, you're on the ball. R is between 0 and 1, and theta is between 0 and 2 pi. That's the unit circle. Okay, so we can set it up now. Theta equals 0. Theta equals 2 pi. Integral. R equals 0. R equals 1. How are we going to convert that one to... There's an easy way and there's a hard way.
R. Negative R.
No,
Right.
that equals R
R.
squared.
R equals
it's-
x squared minus y squared. Or
Almost.
x squared plus y squared.
Okay, so I'm going to come out to the side. R squared equals x squared plus y squared, right?
It's R squared.
Yeah. That's
Oh, negative r squared.
Negative R squared.
So this is negative r squared, so it's 1 minus r squared, r d theta.
Wait. Wouldn't it? Yeah, you're right.
Factor out the negative.
Yeah.
I like it thinking of it that way.
I was thinking it's minus a negative, we should make it positive.
No,
But
it's not.
because your x term is also negative.
Yes. Okay. Yeah, so this is now r minus r cubed. I'm just going to mark that out and put it underneath so I don't have to rewrite the whole thing. Okay. How do you integrate r minus r cubed dr?
1/2 r squared
1/2 r squared?
minus 1/4 r to the 4th.
Perfect.
Yo, that's hot, bro.
Bracket 0, r equals 0. R equals 1 d theta. So let's do it in our heads.
Hello?
If you plug in 1s for both the r's, actually no, I'm going to go ahead and do it this way. That's going to be 1/2 minus 1/4
Which is 1/4?
minus,
So that's
if I plug in 0, what am I going to get?
0.
0.
It's 1/4.
So it's going to be
1/4.
d theta, which is 0 to 2 pi now. 1/4 d theta. I'm down to one letter. I can drop off the theta equals.
1/4 R. Oh,
No.
1/4 theta.
There you go.
Sorry.
So this is 1/4 theta, 0 to 2 pi. Pi halves minus 0, which is pi halves. We did the whole thing without a calculator. That wasn't too bad. Are you getting the hang of this?
Yeah.
Yeah? Okay. Now, we're going to just set this one up, just to save time. Look what it's got here. 1 is less than or equal to x squared plus y squared is less than or equal to 4, and x is less than or equal to 0. So they're not telling me r's and thetas, they're giving me x's and y's for my limits of integration, which I need to convert to r's and thetas. So, having a picture really helps. What do my r's go from in this picture? If I'm talking about this in here. 1 to 2. Agreed? So we can say that R1 is between R and 2, or R is between 1 and 2. I said that backwards. And what about theta? For that shaded part, what is theta between?
Pi half.
Yes, pi halves and 3 pi halves. Are you following what I'm doing?
No, how is it 1 and 2?
Because it says x squared plus y squared is between 1 and 4. So r squared is between 1 and 4. So r is between 1 and 2 because it has to be positive.
Nope, okay,
And then you square root.
X squared plus y squared equals r squared,
correct.
right? Square root that whole thing. 1 is less than or equal to r is less than or equal to 2.
I see it.
That's how you algebraically do it,
That's cool.
okay? Now, set up your integral. That's all I want you to do. Set up the integral.
Hello?
Bless you.
Thanks. Appreciate that. Hello?
All right, we're not going to go any farther than this, but I will say this, that r in the drd theta is going to be your nemesis, just like plus c was last year.
Come on, bro.
You're going to forget it a lot until you finally remember. So, you guys could integrate that, yes?
Yes.
Yeah, if you wanted to factor out the r, you could do that too. Either way.
That's what I was thinking.
Okay. So, questions on that?
Isn't there some, will we ever use trig identity?
Not very much. There was one integral they have here in one of the examples that after you did your first set, it came out to this cosine squared plus something else, and I was like, I don't know how to integrate that. I didn't, seriously. And I looked at the answer in the book and I was like, I don't even know where this came from. So it's like, I'm so glad I can plug it in the calculator and do it that way. All right. Now we're going to move on to, not do this one. We're going to say, what if it's not circles? What if it's not pieces of donut? What if it's something blobby like that? Okay? So the thetas are still going to be numbers. It's going to still go from like pi over 6 to pi over 2. But what's going to change is r is no longer going to be constants. R is going to be equations in terms of theta. So we have an h1 of theta and an h2 of theta. So what's changing? All that's changing is my second integral is going to now be r equals an equation to r equals another equation. Everything else is the same. Okay? Now we're going to d's. Notice it says d now because it's not a rectangle. It's r when all four of the limits of integration are constants. It's d when some of them are equations. Okay? So I'm going to put this is the only change.
Wait, how did they determine heights if the heights vary between point to point?
This up here, wait, I can't point on this thing. This right here is defined by the polar equation.
Okay.
The old polar equation says if I'm at this angle, I'm this far out. If I'm at this angle, I'm this far out.
Okay.
So everything is defined by the polar equation, so we don't need to worry about it.
Okay.
Okay? So, go
So we're not
away.
plugging in heights, we're plugging in the equation.
Right, right. Okay, so now the integrals are just going to be a little uglier. Turn the page. Okay, we're going to start now with where our equation inside is back in terms of r's and thetas to begin with, okay? Our region is bounded by the polar axis and the upper half of this cardioid. and they graphed it for us.
Cardioid.
Cardioid, you remember cardioids? Okay.
Cardioid.
So what you have to do is you can use your calculator. If they don't tell you if they don't give you a graph or they don't tell you what it looks like, get your calculator, put it in polar mode, graph it. So if you want to do that real quick so you can see what we're talking about, practice going into polar.
You guys listen to Playboy Cardioid?
Happy Valentine's Day.
Mode, polar.
I can't see it.
Okay.
I'm calculator.
No, you still can't see. How about that? How about that? No. How about that? There we go. Polar mode. R equals 1 plus cosine x, or theta in this case. Okay, you better be in radians. Do a zoom 7. Actually, let's zoom 7 may be too big. Let's see. Yeah, it's a little small.
Did you already plug it in?
Okay. Now, the thing is, though, okay, you put in the 1 plus cosine theta, but I need to set my window. It says the upper half. It does not say the whole thing. It says the upper half. So the upper half would go from 0 to pi.
Wow.
So window, 0 to pi. I'm going to make my x and min and max go from -3 to 3.
Why?
Because on the picture on the paper it goes to 2.
Oh, okay. That's fair.
-2 to 2. I should have done -3 to 3 is what I meant to do. Graph away. There it is.
Why'd you pick your Y scale to do that?
Because it's a circle and it's symmetric.
What's this?
Okay, this goes out to 2, that goes out to 2. So if I'm going to make my scale go to 3 this way, I want it to go to 3 that way.
Okay, I'll just take that. It's a window.
You may be in degrees.
Hello? Oh, am I?
Make sure you're in radians.
Why don't I have a window here?
Let me teach you a thing or two.
You probably put 3 to 3 instead of -3 to 3.
Did I? I thought I put negative.
Why did you choose that? Why you have
What about my T-step?
Oh, your Y min is your same as your Y max.
That's
Oh, I
what it
didn't
is.
put negative.
You went 3 to 3, like I said. I told you. I told you.
I didn't
Okay.
want to fish that. Bingo.
So,
He's a plate.
in this case,
My name is Fish Fish.
hold on a minute.
I was gonna do
Okay, in this case, we figured out that it goes from 0 to pi, and then from 0 to the curve to make it color. Okay, the curve, honestly, when you graphed on the calculator, was just this part, right? Was just that. But if I wanted to shade it in, I have to say I'm going from 0 to that point. Okay? So, now when we set this up, let's set up the integral. How's this going to go? We're going to do theta equals 0. Theta equals pi. And then we're going to do r equals 0 and r equals 1 plus cosine theta. And then we put in our equation. R squared sine theta RD theta. Yep. Those are too crunched for my liking. Oh, what did I do? Rats. There we go.
Can you scroll up?
RD theta. Can you see now?
Yeah.
Okay. So let's practice this. Take this r in the end, make the r squared and r cubed, and let's go ahead and do the math. I need to bracket this off. So we're going to have theta equals 0, theta equals pi. What's the antiderivative of r cubed sine theta dr? 1/4 r fourth sine theta from 0 to wait, from r equals 0 to r equals 1 plus cosine theta. I like keeping those on there for now to remind me what I'm plugging in for. Especially now when r becomes an equation. This is when you're going to want to go to the calculator after you do your first plug-in. So this will be 1/4 1 plus cosine theta to the 4th sine theta.
What? Oh. Wait, what?
I plugged in the upper limit, the top, the 1 minus cosine theta, goes in place of the r. So it's 1 minus cosine theta to the 4th.
Oh, I see. Okay.
Okay?
Oh, yeah.
Minus 1/4 0 to the 4th sine theta. Now if you can do that in your head, you can know that that's going to just be 0 and it goes away. Okay. Now, just out of curiosity, on my part, do you think that you could do that problem by hand?
Yeah.
Is that a straight U sub?
Oh,
Yeah.
Okay?
Well, no. 'cause,
What would you be?
yeah.
The derivative of cosine is negative, so you put a negative out front.
Right. If that is U, this would be du missing a negative. Agreed?
Yeah.
But I'm not going to make you do it by hand unless you want to. You can do it in the calculator. So let's practice one more time plugging these in.
No.
As long as you're in polar, let's just stay in polar. There are none back there. Are you going for a calculator?
Oh, no.
Okay. So let's go to Math 9. As soon as we turn on the calculator. Can you guys see when I'm writing? No, you can't. So let's go to here. So we're going to type in. Now we can do that y1 thing that I talked about last class. And let me show it to those who were not here. Okay? What you can do is take the r thing, which is already there, and when we type it in the calculator, we're going to use that r. So watch this. We're going to go from 0 to pi. So instead of typing 1/4 1 plus cosine theta to the 4th, we're going to type 1/4 r1 to the 4th. So 0.25 for the 1/4. Alpha trace enter gives me that r1, which is the 1 minus 1 plus cosine theta to the 4th. Wait, to the 4th. And then sine theta d theta. Did you follow what I just did? Yes? Yes? Okay. Boom. We wait 1.6.
What in the name of Jesus?
You forgot to sign theta.
Oh, no, I know what I did.
And if you do it by hand, it comes out to be 8/5. This is R1 to the 4th.
You ready, DJ? Appreciate you.
No problemo.
Okay? How are we doing?
Good.
This is going a lot faster than I thought it would, which is making me happy.
It's because Sam's not here to ask
Yes.
What?
The Sam's not here to ask questions.
And he's going to hear you say that on the video.
Keep it Sam.
All right. The next one is pretty much the same thing. We're going to skip it. Now let's go on to polar area and volumes. Okay? Now we haven't really talked much about this yet, but notice that we're now defining the upper curve that's hanging in the sky as z equals f of r theta. Okay?
We're doing 3 variables.
Well, we have been doing 3 variables, but we just haven't called it z yet.
Oh,
Okay?
why is it so much scarier?
So it just looks scary. I'm going to turn the page. Go away. Turn the page. Okay. Now, does this look the same as what we just did? Look at that. Living.
Yeah.
Look.
Oh, wait.
Does that look just like what we just did?
Yes.
Theta is from A to B.
Yes.
R is from one equation to the other. F of R comma theta, R dr to theta. Volume is the same thing. We just write it with a new name.
A volume is the same thing as.
Pardon?
A volume is the same thing as what?
As the area, okay, is a double integral with polar coordinates. It's basically what it is. So I'm just going to write down that this is the same equation as before. It's like when all of a sudden you're given a word problem that you use a method you've already learned how to do to solve it. Okay. All right, so now, when we dress this kind of problem in the close of a volume, how do we make it work? Look at this next example. Find the volume of the solid that lies under the paraboloid z equals 1 minus x squared minus y squared and above the unit circle on the xy plane. Okay? Okay, so now we're going to just say this equation here is what we're integrating. That's the equation we're integrating. Are y'all listening?
Yeah.
That's the equation we're integrating. And it's above the unit circle. So, Libin, you told me the answer to this last time. What's the r's for the unit circle?
0 to 1.
0 is less than or equal to r is less than or equal to 1. And theta is between
0 and 2 pi.
0 and 2 pi.
Let's go, baby.
So it's going to be that, and the solution, it says, by the method of double integration, it is this problem, and we already did it. And the answer came out to pi over 2.
We did do that.
We did do that problem already. So we just dressed the problem in a new set of clothes, and that set of clothes was finding the volume of a paraboloid over a unit circle. That's all we did. Okay?
Too long.
What you think?
Nice.
All right, let's go a little bit harder. Now the next one starts it on one page, finishes on the next, but the equation's over here. This is a goofy looking shape. Here is my paraboloid,
What the heck?
but we're doing it over a disk that's not centered at the origin. Okay? Kind of hard to see. How clear is your picture?
It's not.
Not very clear at all.
It looks like an upside down.
Okay. All right. Think of this. The one we just did had a circle as a base that comes up, and the top is a paraboloid. It's kind of like the 3D parabola on top. What we've done now is we still have the paraboloid there, the big paraboloid, but we've shifted the disk over.
Oh, so just.
So we're not getting it straight up the center, we're getting it off to the side a little bit. That's what they're trying to show you here.
Like an igloo with a chimney.
Yeah, it's an igloo with a chimney. Okay. I will go with that. Now, the tricky part is the fact that it's not the unit circle anymore. It's the unit circle moved one space to the right. So now we've got to change our limits of integration. Okay? So,
Oh, so,
think about it for a minute.
so the bottom equation is that we have.
So my R theta changes. I mean, my delta R changes.
Okay, so now the r and the theta aren't quite as straightforward. Okay? So we're going to do this in a series of steps. Step 1.
Because it's still the same.
Okay, step 1 is we're going to change the disk to polar. Okay? This is the disk equation right here. That's the base now.
Don't you spell disk with a C?
Hmm?
Do you spell disk with a C?
It can be spelled either way. Compact disc CD is usually spelled with a C.
Because C.
Wait, I've never seen this spelled with a C.
Yes, you have.
Are you serious?
What the heck?
On the
It's like spelling theater two different ways.
It's like a
theatre.
No, I don't know.
I
what
spell
it
theater
is.
with a
Or
R-E.
color with the U.
Yeah, color with the U.
I am dumb.
I don't know what it is now.
Yes, this can be spelled with a C or a K. All right.
Wait, is that what a CD is?
I thought you were
Compact
supposed
disc?
to S.
Yeah, CD is compact disc. Oh, learned something else today, huh?
IQ level 200.
Okay.
Who?
Okay, why is a CD called a compact disc? What was a non-compact disc called?
RAM.
A flash drive?
A record.
A flash drive?
Oh, really? But is that
A floppy
Think
drive?
about it. You know what a record looks like, right? It's like the big black ones
Yeah.
with a record player. Boy, you guys are young. Okay, that was used to be called discs. They were just called discs. They were records. So when they invented the CD, which is this big comparatively speaking, they called it a compact disc. CDs.
Okay, when you just explained it, I was like, wait, a record's already. That's so late. Why is it called compact?
No. Okay, now. Okay, it's your turn to think. Any ideas how to change that to polar?
Substitute out all the variables. Oh no, expand the x and then substitute for the polar form.
Okay, you were on the right track, DJ. I would recommend doing what DJ said, and that is to expand it out, because once I do, I'm going to have an x squared and a y squared, which will turn into an r squared, right?
Yes.
So FOIL out the x minus 1 squared right now. Do it. Okay.
And then you move the constant to the other side.
Thank you for coming to my TikTok.
So what happens to the ones? They cancel out. So the x squared plus the y squared is r squared. Move the 2x over. Because remember, polar equations are r equals something, or r squared equals something.
Oh, you don't.
So what does r squared equal? 2r cosine theta, right? Okay. Now, I'm going to break my cardinal rule. I told you never to divide by a variable because it makes the variable go away. However, in this instance, if I divide by r, that's like r equals 0. And r equals 0 means absolutely nothing in the context of this problem. Okay? So r equals 2 cosine theta is the equation of that circle.
What was the rule that we broke?
Okay, I divided both sides by a letter, and it didn't move the letter to the other side. It made it disappear.
Yeah.
And that's a very dangerous thing to do because you're officially losing an answer.
Oh yeah.
Okay? Now, I'm going to go ahead and do this. Go across the picture.
But does
R squared minus 2r cosine theta equals 0. Watch this. Okay, just watch, don't write. Okay?
say that?
I moved the 2r cosine theta over instead of dividing by r squared by r. I would factor out an r,
Yeah.
and I would have r minus 2 cosine
R
theta
equals 0.
equals 0, and you get r equals 0 and r equals 2 cosine theta, right?
Yeah.
That's what I got for an answer.
It's like,
This answer, in the context of my problem, what is the graph of r equals 0?
a dot.
It's a dot. Does it mean anything in the context of this problem? No. Okay, so in this case, it doesn't do anything wrong to get rid of the r, okay? But actually, if I think about it, that's my lower limit. It goes from 0 to 2 cosine of theta. Ooh, I didn't think about that till just now. Okay, mind blown.
Hello? Did I miss
Okay, so r is between 0 and 2 cosine of theta.
Okay.
Wait, so you found your lower limit by solving for both ends of r?
Yeah, yeah.
What about-
But also I knew that because in order to fill in this circle right here, can you
Yeah.
see what I'm coloring?
Yeah.
My radius could be anything from 0, which is like no radius at all,
Yeah.
all the way out to this radius over here,
Which is essentially 2.
which is 2 cosine of theta,
Oh, that's cool.
okay?
So, given a situation where we cannot plug in r squared, how would we find our...
The radius, the lower limit will always be 0,
Oh, that's cool.
okay? Now, in order to create a full circle, what should my thetas go from?
0 to 2 pi.
0 to 2 pi. Okay? So, the disk itself has now been changed to polar. And I know that when I set it up, it's going to be theta equals 0, theta equals 2 pi, and then it's going to be r equals 0, r equals 2 cosine theta. But now I don't know what goes inside yet. I've been given an equation, but the equation is in terms of x and y. Go back to the top of your picture. It's off my screen. I'm going to pull it down. What's the equation? Paraboloid. Z equals 4 minus x squared minus y squared. So now step 2 is to change the paraboloid to polar. Change the paraboloid to polar.
Wait, how did you figure out the limits for the theta?
Because it's a full circle base,
Gotcha.
I have to do all the way around the circle. Say it again, Andrew. 4 minus r squared. Do y'all see that? This is 4 minus r squared. Done. That was easy. Okay. So that's what goes in the integral. So we now write 4 minus r squared. And what else?
R.
RD theta.
RD.
RD theta. RD theta.
I feel like a pirate.
What's the parent's favorite letter?
It's his favorite movie rating too.
It's the C.
Stop.
That was pretty good. Come on, no cap.
Okay. How you doing? This isn't so bad, is it?
Well, what do we do? Homework?
Yeah. Yeah, homework's a different story, right?
Yeah.
Okay. Now, we are going to go ahead and finish this one out. Because it's going to do something goofy. So I'm going to show you how to get around goofiness. All right. So this is 4R. Why do I like goofy? I don't like it. It just happens.
You want stomachers? I didn't have this. Leave it alone.
Okay. So, theta equals 0. Theta equals 2 pi. Integrate. What's the integral of 4r minus r cubed dr?
4R, 1/3R. Oh, sorry.
2r squared minus
Looking at the original, I was like, what is your
1/4 r to the 4th from 0 to 2 cosine theta. Bless you.
Thank you.
D theta.
God bless you, bless you.
Such a racket.
Bless you, bless you.
So this is now 0 to 2 pi. When I plug in r to be 2 cosine theta, what is my coefficient in the front going to be?
Right, no,
8.
8.
It's 8. 2 squared times 2 is 8 cosine squared theta minus 1/4 cosine to the cosine theta to the 4th. Did you follow all that? I messed up. What did I do?
This is supposed to be a 4, not an 8.
Yeah, the one in the.
I forgot the 2 when I plugged in the cosine the second time.
Hello?
So this is not right.
What?
I'm supposed to be plugging in 2 cosine theta to the 4th. What is 2 to the 4th? 16 times the 1/4, so this really isn't 1/4,
4.
it's 4
It's a 4.
cosine to the 4th theta. There we go. Okay, minus, if I plug in 0 for r,
0.
this is going to be all zeros. Okay,
Wait. You did. Oh, because when you plug in the 0, those terms disappear.
yes.
So you move straight into 2 cosine theta. Okay, I see it. I see it. I see it. Oh,
Okay, so now, I tried to do this by hand, and guess what? It doesn't work. So, to the calculator. I want you to try to plug this in. Make sure you plug it in right. Right now. Okay. Use the R if you want to for 2 cosine theta. It's much easier.
So what?
Bless you.
Let's see.
I will tell you what the answer is. I know what it is as a, in terms of pi, but I'll tell you what it is as a decimal.
Is it not -8? Hold on.
You plug in the 2 cosine theta first.
Yeah, but wouldn't it be, because it would be the zero term minus the 2 cosine theta?
No, top minus bottom.
Oh, where am I?
Oh, do you have to put
Yeah.
the square after the parentheses in the calculator? Okay.
Yes, you have to put the squared after the parentheses in the calculator.
No. It's the direction my follicles. Did you just make fun of the way I said follicles?
Sit here. The answer is a number.
Bro, we're gonna like be in advanced math.
You guys get
We're
going?
gonna type in an equation that's even a calculation that's less than letter.
I'm busy.
We're doing good. I think I may finish. I'm so excited. Okay, what are you getting as a decimal answer?
15.707.
Nope.
15.
Oh, majority rule.
Nope.
I got it in 15.
16.
All right, let me do it myself.
Minus 4 plus theta.
Wait a minute. What is this? I'll put extra parentheses.
I don't know.
But the funny thing is, I'm kind of doing it.
It's got 13 is
The kind is kind of.
Oh, that would make, that's gonna make it worse. Okay, never mind.
Not 50.
Yeah.
The R thing doesn't help.
Wait, we're still in polar. Does that affect?
Sorry, I'm gonna keep it confident.
Yeah, you've gotta be in polar. Did you leave it, did you plug it in with the cosines or did you plug it in with the R's?
Cosine. Theta.
What? It's still there.
Yeah, I still got 2.707.
Wait, what'd you get?
Oh, it told me non-real answer. That's nice.
What'd you get, bro? You got 15.707?
Yeah.
Me too. What'd you get?
50.707. That's it.
Yo, that's what I got. Did you get? Oh. What? Yeah.
Hold on.
Wow,
Oh, I put it to the theta power. I did that last time. Why did I do that?
Monster bacon.
Hey,
Okay, the book lied to me. The book lied a lot.
did you get 15.7?
I did get
So I
15.7.
kinda.
And the book told me it was 5 pi over 2.
It's going to.
That's 5 yeah.
Okay, it's just 5 pi.
I kinda.
So it's half of that.
It's half of that. It's giving me double the answer. Okay, hold on.
Oh, because the limit, like,
Oh wait, it's
Zero.
because of the way it's like cut off.
Yeah.
No, I have a thing. No, I think it may have to do that we may only have to go 0 to pi. Let me check.
I was about to say that. What if the limits of integration are 0 to pi instead?
That's what I'm wondering.
It's never gonna be
Yeah, because look, you're only using the positive x-axis.
Oh, okay. Go into polar y equals. Go into polar y equals where the r equals is. If you have not done so already, type in 2 cosine of theta. Okay? I want you to change your window to 0 to pi. It may already be changed. You may have changed it before. Graph it and see if it gives you a full circle.
Yeah?
yeah.
Yeah.
Yes. So we messed up assuming it was 0 to 2 pi. We were able to go around the whole circle in pi instead of in 2 pi. So that is a mistake on my part.
How would we know though?
You would have to graph it and see. Okay, another way you can tell, here's how you can know. 2 cosine theta equals 0. Set it equal to 0. So it's got to go all the way around.
Cosine theta equals 0, theta equals pi.
Theta equals 0. Okay. It has to go all the way around twice. So where does cosine equals 0?
Pi.
Zoo, pi, and 2 pi. Okay. I'm trying to think. I'm wondering if because it's 0 to pi.
No, because it's only on the positive x-axis.
No, that's wrong. Pi has, that doesn't help. Never mind. Thought this would help. Forget that. Okay.
I mean, graphically, it's only on the positive x-axis.
It's only on the positive x-axis.
Yeah, so you wouldn't need to consider
Wait, what?
the negative half.
Very interesting. Oh. Okay, I'm wondering, I'm just thinking out loud here, guys. Give me a minute. 2 cosine theta, if you were to graph it as a wave, what does the 2 do?
It makes it,
It makes it twice as tall, right?
Yeah.
Goes from 2 to negative 2. So basically, you get as much area. I'm trying to think. Maybe. I don't want to spend too long on this because I want to finish the notes. That's funny.
What is number references?
Huh?
We just won't reference it.
Yeah.
Algebraically,
Okay.
I don't see it, but graphically.
So this is supposed to be pi. Change it. Whoops. Boy, that was messy. This is supposed to be pi.
Oh, because there's only half of a graph.
Boom.
Literally,
That's, yeah.
Yeah.
What?
literally.
Okay.
Just process.
So it is 15. What was it? 15 point what?
70796.
7 what?
15.70796.
708 then. Okay.
Cool.
That's what I wanted. All right. Moving on. Next page.
Wait, so it's not going to be half of that?
Oh, it is going to be half of that.
Yeah.
Okay. Sorry. Supposed to be half of that.
7.854.
Thank you. So we need to change the limits. I'm going to make a note of this. Change the limits. 0 less than or equal to theta, less than or equal to pi. So those who are watching will know what's going on. What are you doing, Ms. Bell? I don't know. Yes, I do. Okay, since I'm going to have to make a beginning of the video, I will make an end of the video if I have to, if I don't finish. Okay? And I have to finish at 5 after because I haven't picked the problems for you to do yet, and I got to do that.
I mean, that's cool.
All right. No. Or I could, how about I send it to you at the end of the video?
Bingo.
That'll work. That'll work. Okay. So, now, the next example is ugly, and they're talking about sometimes changing to polar is not the best idea. Okay? Notice that the base is a triangle. Triangles don't translate to polar very well. Circles do, but triangles don't. This is not a good polar problem. And they go through, and it's written in there, and it does all the math in polar and shows you, yuck, this is gross. Sometimes it's good to have somebody else do all the yucky math and discover it. That's not the way to do it. So they did the problem. As you can see, this integral is very complicated.
Hello?
So they go back and do it in rectangular, and it takes them 2 steps, and they're done. So thank you very much.
Looking forward.
Oh, God.
Okay. In the next problem, they go through and they talk about finding the volume inside a cone. Okay? And basically what it does is as they do the math, it creates the exact formula for the volume of a cone, which is 1/3 pi r squared h. We did that last year with the volume of revolution. They do it with double integrals.
Yeah, that sounds so much better though.
Okay? Now, do you remember last class that we talked about if we want to just find an area, we integrate 1 RD theta.
Oh, yeah.
Remember we talked about that? Because if you use your r's and thetas to just define your base, and your height is 1, the volume is going to be area of the base.
Area of the base.
Okay. So,
What the heck?
now we're going to do the next one. This is, I think, the last problem.
1 times dA. That's the same thing, right?
1 dA, 1 RD theta, yes. Okay, the next one, they start at the bottom of the page, we finish on the next page. It's a polar rose. Okay, turn the page. Polar rose. Remember these little guys?
Yeah, find the area of 1 times 8.
Okay, so basically what we're going to do is we're going to do a double integral. We're going to set up a double integral to do this. Now, I don't want to do all 8 petals. I would rather do 1 petal and multiply by 8. Does that make sense?
Yeah.
Okay, so what you have to do is to find your theta Notice that every petal starts and stops at 0, at r equals 0, which is the center of the rows. So we take the equation and we set it equal to 0. We want to know when it hits the origin. Okay, how do you solve this problem?
Cosine inverse.
Cosine inverse. So 4 theta equals cosine inverse of 0. 4 theta equals, where is the first place that cosine equals 0? Pi halves, right?
Yes, what I said?
What's the next place that equals 0? 3 pi halves. Now, you only need 2 of them. I'm going to put a dot, 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 because it does go on and on forever and ever. But now I need to solve for theta.
Divide by 4.
Divide by 4,
What's next? And multiply by 4.
which is by same thing as multiplying by 1 over 4. So this is pi over 8 and 3 pi over 8. And that's your limits of integration for this problem. Okay, we're finding the area of this thing. So it would now be theta equals pi over 8. Theta equals 3 pi over 8. R equals. I'm going to scoot up.
Thank you.
What do you think my lower limit of R is? I already told you what it's always going to be. 0. And the upper limit is cosine of 4 theta, the equation that I'm doing.
Huh? I thought the equation was for it.
No.
Oh wait, no.
This is area. This is 1 RD theta.
Oh.
We're finding area using a double integral. So what I may do is ask you just to set it up. Okay?
Why'd you pick that for your R?
Because that's the equation of the rows. When you do area,
Oh, yeah.
the lower limit is 0, the upper limit is the curve that you're finding the area of.
Right.
Okay? So you do the math, and it all works out. Now we're going to do the next one, the last problem. What time is it? Oh, awesome.
Let's go.
Okay, I'm going to finish. Okay, remember doing these last year? Finding the area between two curves?
Yes.
Yuck, yuckity, yuck, yuck. Remember I told you it was like the sprinkler? I went to Clemson and somebody said, this is like a sprinkler. I went, oh my gosh, that's brilliant. So they walk you through it. We don't have to write anything down. We're finding the area enclosed by both the circle 3 cosine theta and the cardioid 1 plus cosine theta. Whoa, come back here. 3 cosine theta, 1 plus cosine theta. Okay? First thing you do, you set them equal to each other. Set them equal to each other. And you find out that it intersects at pi over 3. And then you say that you can do that on the calculator, I think. Oh no, I have to do it by hand. The area above the polar axis, what did you just do? Goes from 0 to pi over 3. Outer minus inner is the curve, is the orange curve. Because this, hang on, this is pi over 3. So from 0 to pi over 3, yes, where they intersect, is the cardioid. And then the rest of the way to pi over 2, which is back down here at the origin, the outer curve is the circle. So it's going to be 0 to pi over 3 of the cardioid plus pi over 3 to pi over 2 of the circle.
I don't understand where pi half came from.
It's just that's.
Okay, pi halves is when I'm going to hit right here on the circle. If I set the circle equal to
Circle.
the dark circle. 3 cosine theta equals 0 at pi halves. So what that means that when the radius is 0, i.e. when I'm at the origin, the angle theta is pi halves.
Do you get that? I'm not getting that.
Okay,
No, I'm not following at all.
3 cosine theta equals 0. Agreed?
Cosine theta. Yeah.
Cosine theta equals 0. Theta equals pi halves.
Okay.
Okay?
I get that algebraically.
So, 0 is where the r was. Because r equals 3 cosine theta. That's the equation of the curve.
Okay.
Right? Okay. So, when r equals 0, that means, you just told me a minute ago that r equals 0 is a point.
Yes.
That point happens to be right there at the origin.
Okay.
So when I'm on the circle at the origin, theta is pi halves.
Okay. But graphically, what is that?
What that means is, when I plug,
Circle,
Yeah.
that's pi half. This is approximately pi theta or whatever. This right here is always pi half.
Oh, I
Oh.
see
It
it.
is
Yo.
oh, you see it? Okay, okay.
Yo.
Thank you, Caduce.
Appreciate that. I see
Yeah,
it.
that helps.
Yeah.
Because I'm going to do it on the video for those who didn't see it. This is the line pi halves, right?
Yeah.
What's the y coordinate? What's the r coordinate? What's the radius at pi halves? It's 0.
Yeah.
Yeah.
Oh, gotcha.
Okay, good job.
Yo,
Thank
that
you.
helped a lot.
That helped a lot. Okay. So, then they come down here and they set them up. Why is there a 2 there?
That's the thing.
Why is there a 2 there?
Top and the bottom.
Top and the bottom.
Oh, I didn't even see that.
I only did the top and the, okay. This 2, you might want to draw an arrow and say this is the top and the bottom. And then they worked it all out, and they got 5 pi over 4, and that's the answer. Okay, so you're going to need to probably look at that a little bit more to make sure you get it. All right, so we're going to stop with that.
Solid.
How are we doing? Don't close up just yet.
Could you explain in terms of like how the sprinkler would work?
Okay, yes. Okay, let's do that. Good idea. Okay, the sprinkler starts at 0, which means it's starting on this axis, and it's going. And which curve is it always hitting? The cardioid. Until I get to pi over 3. Then after pi over 3, what's it hitting? The circle.
Oh,
Until I get to pi over 2.
okay.
That's why it breaks apart.
Okay, that makes sense.
Okay. So that's that. Now I think I'm done. Let me make sure. I am. So the rest of the pages are basura.
Basura.
We only have one.
Oh wait, you only have one. I'm creating more pages as I go. That's really dumb. I hate this thing. I hate it when it does that. No wait, I don't want to edit. I don't want to do that. I want to edit and get rid of all of these. All right, guys, you have the homework. I will send you a video with the beginning and what the problem numbers are going to be. Have a great weekend. Trash, trash. Thank you, ma'am. Shelley, do you know where your calculator is? Okay. Do you need to check one out?
Oh, no.
Okay. I'm saying if she needs it and you need one too, I can check you one out. Okay. I'm so glad I finished. That's been a first.